In this video, we'll be looking at the Poisson distribution. So what is a Poisson distribution? A Poisson distribution is a discrete probability distribution. The discrete random variable x follows a Poisson distribution if it counts the number of events that occur at random in a given time or a space. For a Poisson distribution to be valid, it must satisfy the following properties. Event occurs singly and at random in a given interval of a time or space. The mean number of occurrences in a given interval lambda is known and finite. Lambda has to be positive but does not have to be an integer. And each occurrence is independent of the other occurrence. If x follows a Poisson distribution, then it is denoted as x has a Poisson distribution of lambda. Lambda is the mean number of occurrence of an event. The formula for a probability of r occurrence in a given interval is probability of x is equals to r equals to e to the power of negative lambda times lambda to the power of r divided by r factorial. R can be 0, 1, 2, or any integer number, as the Poisson distribution is a discrete probability distribution. E is the Euler constant, and it's approximately 2.718. And R factorial is R times R minus 1, R minus 2, all the way to 1. Is a 5 factorial means 5 times 4 times 3 times 2 times 1. What are the important properties of a Poisson distribution? The mean and the variance of a Poisson distribution are equal. The distribution can be represented visually using a vertical line graph. If lambda is close to 0, the graph has a right-hand tail positively skewed. If the lambda is bigger than or equals to 5, then the graph is approximately symmetrical. The Poisson distribution becomes more symmetrical as the value of the mean lambda increases. Let's look at some examples based on what we have learned on the Poisson distribution. Example 1. The random variable x has a Poisson distribution of 2.1. We need to find p probability of x equals to 3 and probability of x bigger than equals to 1 and probability x in between 1 and 4 included. We'll start with the first one. We are looking for a probability of x being 3, and that's the case where we have the probability of x being r, so that is e to the power of negative lambda and the lambda to the power of r divided by r factorial. So if I apply that formula to here, so I know that the lambda is 2.1 from the given statement, and I know that r is 3. So I can say e to the power of negative 2.1 multiplied by lambda 2.1 to the power of r3 divided by 3 factorial. If you put this into your calculator, you're going to have approximately to 4 significant figures 0.1890. So that's basically done using the calculator. Part B says the probability of x being greater than or equals to 1. On a binomial distributions, we learn the cases for the cumulative distributions that I can write this probability of x being greater than or equals to 1 and since x is a discrete random variable, if I minus if I write 1, take away the probability of x being less than equals to 0, that's the same case where the probability of x being greater than equals to 1. So remember, x is a discrete random variable where no matter what, up to what number it goes, so you basically minusing it, what it is x less than equals to 0 or like less than equals to, minusing it from 1, so that gives us the probability of x being greater than equals to 1. In another word, we know that the probability of x being greater than equals to 1 plus the x being less than equals to 0 is always equals to 1. The probabilities add up to 1 all the time. So I need to take x being less than equals to 0 because I'm including x being greater than equals to 1 here. So the one left is x being less than equals to 0. In fact, this is just the x equals to 0 because x can be 0, 1, 2, 3 and all the way up, all the natural numbers including 0. So x being greater than equals to 1 plus x being 0 is equals to 1. Alright, so since x being 0 is the same as x being less than equals to 0, let's write it there. So now I can say now if I use the formula again, that's going to be 1 minus e to the power of negative 2.1 and lambda to the power of 0 divided by 0 factorial, which is the same as 1 minus e to the power of negative 2.1, which you use the calculator for this and you are going to have 0.8775. So part C is x is in between. We are looking for probability of 1 is smaller than x smaller than equals to 4. So remember, the x is a discrete random variable. So in this scenario, x can be 2, x can be 3, or x can be 4. So you can say that this x is being between 1 and 4 inclusive. So you can say that x can be 2 plus x can be 3 or x can be 4. I'm adding up all the probabilities because those are the scenarios that we use, or in between. So x is being between 1 and 4 as an x discrete random variable. So the x can be 2 or it can be 3 or it can be 4. So to find the probability of x being between 1 and 4 inclusive, we can just find the probability of x being 2 and add it to probability of x being 3 and add it to probability of x being 4. So we are again going to use the same formula, e to the power of negative 2.1. That's 2.1 squared, that's divided by 2 factorial, and plus e to the power of negative 2.1 cubed over 3 factorial plus e to the power of negative 2.1 and multiplied by 2.1 to the power of 4 divided by 4 factorial. So if you calculate this all using your calculator, you're going to get approximately 0.5583. Of course, that's not the best way to do that. Just like a binomial cumulative distributions, Poisson also have a cumulative table. In the next example, we're going to solve this kind of problems like given with the inequalities using a cumulative table. Starting with the first one, and in the example, you're going to learn how to use the cumulative table. In this example, x has a Poisson distribution of 5, so we know that the lambda is 5. So we are looking for x being less than equals to 3. So the probability of the probability of x being less than equals to 3. So for this, you just open the formula booklet and open the Poisson cumulative distribution, and you are looking for the lambda being 5. So lambda being 5 is here, and we want x being less than equals to 3. So that's sum of the probabilities up to 3 is here. So the intersection is 0.2650. So the probability of x being less than equals to 0, less than equals to 3 is 0.2650. Part B, the probability of x being greater than equals to 2. Just like we did in the binomial distribution, this is the same as 1 minus the probability of x less than equals to 1. So this is 1 minus probability of x being less than equals to 1. So it is this one. X is this one. So let me put this color over here. Lambda is still lambda is still 5. So we are going to be using this probability 0.0404. 0.0404. So that is approximately equals to 0.9596 if you use your calculator. In part C, the probability of 1 being less than equals to x less than equals to 4. This can be written from the binomial distribution. We know that x is less than equals to 4 minus the probability of x being less than equals to 0. So we take the 0 over here because we do include 1. Okay, so again we are going to use the distribution table, cumulative distribution table. So x is being 4, the same lambda stays the same, x is being 4, so that gives us the probability up to 4, 0.4405. That minus, so x is being 0, gives us the probability 0.0067. So that's approximately is equals to 0.4338. So remember, when you're using a cumulative distribution function for Poisson, remember that to find the lambda, which is mostly going to given in the question, or you work out the lambda value, and then when you look at the table, you just make sure that you're finding the probabilities, the corresponding lambda values. So lambda values in the table goes up to 10, and of course you have your calculator for other values of lambda, or you can actually work out this probabilities just writing a little bit of solution using your calculator as well. But remember to give the solution until the point where you are forced to use a calculator or a table. And the last example is we're still going to use the table. So let me bring that table down. So okay, so the first, that the lambda is 7.5. So we need to use a lambda value which is 7.5. Let's just highlight this. So they want us to find A, B, and C. So for the first one, probability of x being less than equals to A gives us 0.2414. So lambda is being 0.75. All you have to find this value in the table, and the probability is 2414. So that gives us the x must be less than equals to 5. So we say that if x is less than equals to 5, that gives us the probability 0.2414 from the table, so the A must be 5. So for the part B, the probability of X being less than B is equal to 0.5246. So we know that this probability, X being less than B, can be written as probability of X being less than equals to B minus 1. B isn't included, so we just take 1 below. So that's equals to 0.5246. So all we have to do is find 0.5246. 5246 is here. That gives us the value 7. So we're gonna say that B minus 1 must be then 7. So the B must be 8 in order this statement to be correct. Part C is where the probability of X being greater than equals to C. Is it greater than equals to C? Yes. It is equals to 0.3380. So this can be written as probability 1 minus the probability of X being less than or equals to C minus 1 equals to 0.3380. So then we can say the probability of X being less than equals to C minus 1 is equals to 1 minus 0.3380. So the probability of X being less than equals to C minus 1 is equals to, so all you have to calculate, the 1 minus 3380 is going to be 0.6620. So now we find this in the table. 6620 is just below, so we're going to say that that means C minus 1 has to be 8, so the C must be 9. Alright, so that's the end of all the examples that I do. Alright, so hopefully you understood how to deal with the Poisson distribution. It's almost like when you're solving the question, it's almost like a binomial distribution with a difference.